Hello, this is lesson 5 on conditional probability, section 3.2. We will start off with a brief review of some of the intro to probability material from the previous lesson. Let E be an event of an experiment with sample space S. The probability of the event E is equal to the number of outcomes of E divided by the number of outcomes in the entire sample space, all the possible outcomes. The probability of the union of two events, A union B, is the probability of A plus the probability of B minus the intersection, probability of the intersection. The U-looking symbol, union, in math, that refers to and or, at least one, A or B or both. The intersection, upside down U symbol, is just and. It's only the overlap, only what the events A and B have in common. The union, the probability of A union B will involve addition and subtraction. The intersection will be multiplication. We're going to get to those formulas coming up now. Consider a compound experiment, two parts. You're flipping a coin first and then rolling a single die. Find the probability of flipping tails and rolling a 3. And then we'll look at the probability of flipping tails or rolling a 3, the union here. So the probability of tails and 3, it turns out in this particular case that we can just multiply the probabilities. The probability of tails is 1/2. The probability of rolling a 3 is 1 out of 6. The product is 1/12. There are certain cases where we have to be a little bit more careful than that. We're going to get to that later in the lesson here. If we scroll down to the diagram here, we see that of the 12 outcomes in the sample space, there's only exactly one of them that has the T, has both the T and the 3. So we only have one way to achieve this out of 12 possibilities. All right, now we'll move to the second part, part B, the or situation, the probability of tails or a 3. So the formula is to do the sum, probability of tails, plus the probability of 3 minus the probability of T and 3, which we just found to be 1 out of 12. The probability of tails is 1/2. The probability of 3 is 1/6 minus 1/12. Using a common denominator of 12, we get 6 over 12 plus 2 over 12 minus 1 over 12 is 7 over 12 for T or 3. So we see that we have 6 out of 12 outcomes that contain the T. We have 2 outcomes that contain the 3. But one of them is circled twice, and it's not a unique element there. So it's the same element twice, so we have to subtract that one out, and that's why we're left with 7. So there's only 7 ways here to achieve this union T or 3. So that's 7 out of 12. Okay, last time, lesson 4, we briefly hinted at this question. If we assume the probability of rain is 0.30 on any given day, we have to make an additional assumption about independence, which we'll talk about a little later. What's the probability of rain on Saturday or Sunday? At least one, Saturday or Sunday or both days. So it's the probability of rain Saturday plus probability rain Sunday minus the overlap because we're double counting. So probability for Saturday is 30%, 0.30, Sunday's 30%. For the probability of both, we multiply those together, 9, 0.09. 0.60 minus 0.09 is 51. So it's 0.51. The probability of rain is 30%. The probability of no rain is 70.70. The complementary event, 1 minus 0.30. So if you went out case by case, rain on both days is 0.09. Rain on exactly one day is 0.21 because you're doing 0.3 times 0.7. Same thing for the other order. Rain first on Saturday and no rain on Sunday is also 21%, 0.21. No rain on either day is 0.7 times 0.7. And so for this particular question here, we're talking about rain on at least one of the days, so we're going to include all of these that has at least one R in it, and that will add up to 0.51. Okay, now we get to this new topic here, conditional probability. First example, you draw 2 cards without replacement. Find the probability both are kings. So there are 4 kings in the deck, 52 cards total. Now, this is the key thing here. Because it's without replacement, on the second draw, we only have 3 kings left out of 51 cards. So it's going to be 4 over 52 times 3 out of 51. And just get that multiplication dot in there. You're going to multiply those together. But here we're seeing a conditional probability in the sense that the probability of the second king is different than the first king because the card was not replaced. We have an altered probability there because the first king was removed. And notice that this does look like a permutation, a mini permutation. Numerator is 4p2, denominator is 52p2. So you can also think of it as a permutation here. If you want to view it as an ordered situation, without replacement would be ordered without repeats. And so it's a permutation, 4p2 divided by 52p2. All right, second example. If we roll a pair of dice, what's the probability the sum is 10 given the first roll is 6? So if the first roll is 6, the only way to end up with a total of 10 would be that the second roll would have to be a 4. The probability of that 4 happening is 1 out of 6. If we roll one die, what's the probability that it's a 5 given that we know the roll is odd? So that vertical line reads as given. We're assuming that we know that the roll is odd. So what's happening here is we're basically decreasing our sample space. When you roll a die, you would typically have 6 possible outcomes. but we're restricting to just the odd ones. So that reduces things down. That reduces down to only 3 possibilities, 1, 3, and 5. So in that reduced setting, there's one way to get the 5 out of 3 odd values, leaving us with a probability of 1 out of 3. All right, now the official formula here for conditional probability. The probability of A given that B has occurred is the probability of the intersection of the events, probability of A intersect B, divided by the probability of the given event B. Sometimes the textbook uses shorthand notation. It doesn't write the intersection symbol. It just writes probability AB. So what's happening in the conditional probability is, as I mentioned before, we're reducing the sample space. Basically, our new denominator is working solely with the outcomes that contain B. So going back to the previous example in a little bit more technical detail here, the probability single die rolling a 5 given odd. It's the numerator is the intersection 5 and odd. Denominator is the probability of 5. The probability of 5. I'm sorry, that's incorrect. The denominator should be the one that's given. That's the probability of odd. Probability of odd, yeah. It's the probability of A given B is the probability of the intersection divided by the probability of the given event. So numerator is the overlap. Now 5 intersected with odd is still just 5. So that's 1 out of 6. Odd, the probability of an odd number is 3 out of 6. And then the 6's cancel out, and we're left with a value of 1/3, which is what we got initially. Now we're going to revisit the second example. Sum is 10, given the first roll is 6. So it's the probability of the overlap. Roll 1 is 6 and the sum is 10, divided by the probability that roll 1 is 6. The probability that roll 1 is 6 is really 1 out of 6. I converted that to 6 over 36 just to have a common denominator. You'd still get the same answer either way. Now, the numerator is 1 out of 36. There's only one way to have the first roll 6 and the sum 10. It has to be the ordered pair 6 first, then 4. So there's only one way to achieve that out of 36. 36 cancels out. You're left with 1 out of 6, which is what we had the first time. All right, number 4. We roll a die and we want to do the conditional probability here, the probability of odd given prime. So some definitions here. The odd values here are 1, 3, 5. Prime numbers, a little bit tricky here with this one. Prime numbers are positive numbers that have exactly 2 positive factors, 1 in itself. So technically 1 is not prime. So 2, 3, and 5 are prime numbers. 6 is not prime. 6 can be factored as 6 and 1 and 3 and 2. 4 can be factored as 4 and 1, but also 2 times 2. So we want the probability that the value of the roll is odd given that it's prime. So we're shrinking our sample space down to just the prime numbers. Out of the 2, 3, and 5, how many of those are also odd? There's an overlap of 2 there. So that's where this 2 is coming from. So there's a 2 out of 6 chance of getting an odd and a prime, 3, 5. That's 2, 6. The probability of getting a prime is 3 over 6. And the 6's cancel out. In a lot of these problems, if you keep track of your common denominator, you can kind of skip over that division by the total number of outcomes there and go directly to the 2/3. All right, we're going to look at part A of one of these textbook exercises, 3.28. Suppose that an ordinary deck of 52 cards is shuffled and turned, and the cards are turned over until the first ace appears. Given the first ace is the 20th card, what's the conditional probability that the next card is the ace of spades? So we're going to do this a shortcut, and then we'll go by the formal definition here. So the shortcut is as follows here. We know that the 20th card is the first ace, so we know it's one of four cards, the four aces. We have club, spade, heart, diamond. Now, if we want the next card to be the ace of spades, the only way that could happen is if the 20th card was not the ace of spades. So it would have to be one of the remaining aces, the other three. Has to be one of the other aces. We know the 20th card was the first ace. If we want the next card to be the ace of spades, we need the 20th card to be one of the other aces. So there's a 3 out of 4 chance of that happening. Now, on the next draw, you want to get the ace of spades. There's only one way, there's only one ace of spades in the deck. And how many cards are left? We've removed 20. There's 32 cards remaining. So the possibility of getting that next ace of spades is 1 out of 32 after the 3/4 to make sure we didn't get it on the 20th selection. So it's just 3 over 4 times 1 out of 32, which is 3 over 128. So again, that's kind of quick. That doesn't always mean it's the easiest way to understand it, but that's this seems to be the fastest way to do this problem. So to recap, we know the 20th card is the first ace. We want to avoid the ace of spades, so it's there for the 21st selection. So we're going to restrict ourselves to missing that ace on the 20th draw. That's 3 out of 4. Pick one of the other aces, then pick the ace of spades next. One way to do that out of 32 cards left, and then multiply that out. Now, the long way here to do this here, it's going to look kind of messy, but we do end up in the same spot. So by definition, it's the probability of the conditional probability A given B, probability of the intersection divided by the probability of B. Now, the given information here, the B event, was that the 20th card is the first ace, and then we want to find the probability of A given B, where A represents the 21st card is the ace of spades. So to figure out the probability the 20th card is the first ace, we have to make sure that the first 19 cards are not aces. So in order to do that, we're going to select from the remaining cards. There are 4 aces in the deck. 48 cards are not aces. So we're going to select 19 cards. The first 19, we're going to avoid the ace. So it's 48, choose 19. Out of a grand total of 52, choose 19. That's the overall number of possibilities for choosing 19 cards. And then we have to get the ace on the 20th card. There are 4 ways to do that, and there are 33 cards in the deck after removing 19. So this is our denominator. The 20th card is the first ace. So to recap, first 19 cards avoid the ace, choose directly from the 48 non-aces, then get the ace on the 20th card, which is 4 out of 33. Now, the numerator is the overlap. The numerator is doing all of the restrictions of B, but also getting the next card to be the ace of spades. So the first part's identical here. The first 19 cards cannot be an ace. So it's 48 choose 19 over 52 choose 19. Then we have to get the ace that's not the ace of spades in the next draw. So that's where the 3 out of 33 comes from. And then finally, the next card has to be the ace of spades, 1 out of 32. And then everything cancels out, and we're back to our shortcut. The 48 choose 19 cancels out. 48 choose 19 is canceled. 52 choose 19 is canceled. And the 33s cancel out. And we're left with what we had in the shortcut, 3/4 times 1 over 32. All right, now the definition here of independent events, which we have been hinting at. We assumed independence on the rain problem, flipping the coin, rolling the die. Those are independent. So what does it mean to be independent? The probability of A given B is equal to the probability of A. The probability of B given A is the probability of B. So the occurrence or knowledge that B has occurred does not impact the probability of A happening. Knowing that B occurred does not change the probability of A. So that is the definition of independent events. The occurrence of one does not affect the probability of the other, and vice versa. So putting this into the conditional probability formula and cross multiplying, this is an equivalent form for independent events, that the probability of the intersection is equal to the product. So when events are independent, the probability of the intersection is just equal to the product of the individual probabilities. In general, if you don't have independent events, then you have to use conditional probability. The probability of the intersection is probability of B times conditional probability A given B, or probability of A times the probability of B given A. And we saw this. We saw this way up here, way at the beginning. We saw this here when we selected two kings. This 3 out of 51 is essentially a conditional probability after the first king removed. Second king has an altered probability. I prefer, in this particular context here, I kind of think of that as really the trials are fail to be independent there because the card is not put back. So again, independent events, probability of A given B is equal to the probability of A. Another computational usage of independent events, the probability of A and B is equal to the product of the probabilities, probability of A times the probability of B. We use that up here in this example up here, flipping tails and rolling a 3. Flipping the coin, rolling the die, those do not impact the probabilities. They're independent events, so we can just multiply the probabilities a half times 1/6. Okay, up next is the concept of mutually exclusive events. Basically, mutually exclusive means that the events cannot happen at the same time. They have no outcomes in common. Their intersection is empty. A intersect B is empty. When that happens, the probability of the union is just directly the sum, probability of A plus the probability of B. Recall that in general, when you're finding the probability of a union, you do add, but then you have to subtract the overlap. But in this case here, if the overlap intersection is empty, that probability is 0 and that term drops out. Okay, next example here. Now we're rolling a pair of dice, so there are 36 outcomes, and the calculation is the probability that the sum is 6, given that the first roll is even. So we, using the formula here, we want the probability that both of them happen, sum 6, and the first roll is even, divided by the probability that the first roll is even. So the probability the first roll is even is 3 out of 6. There are 6 outcomes in the first roll, 1 through 6, and 3 of them are even, 2, 4, and 6. If you want to make a common denominator, it's 18 out of 36. Now, numerator, we want the sum to be 6, and we need the first roll to be even. So looking at this sum 6 row here, looking at this row, we see that there are 2 ways for this to happen, 2, 4, and 4, 2. So there's 2 ways to satisfy the intersection there, 6 and R1 even. So that's 2 out of 36. Common denominator divided by 18 over 36. The 36's cancel out. And we're left with 2 out of 18, or 1/9. So the probability that the sum is 6 given roll 1 is even is 1/9. Now, how does that compare to the probability that the sum is 6? The probability the sum is 6 is going to be 6. Excuse me, it's going to be 5 out of 36. There's 5 ways to win out of 36 total. These numbers are not the same. These are not the same, so these events are dependent. So what happened here is the probability went down ever so slightly. 1 out of 9 is 4 out of 36 instead of 5 out of 36. Now, if we change the sum to 7 instead, interestingly enough, the events are independent. So the probability that roll 1 is even, that's still 3 out of 6, or 18 out of 36. Now we want the sum to be 7 and roll 1 to be even. There are 6 ways for the sum to be 7. And of those, we have exactly 3 of them that start with an even number. And so that probability is 3 out of 36. The 36's cancel out. We're left with 3 out of 18, which is 1/6, which is the same as the probability that the sum is 7. That's also 6 out of 36, which reduces to 1/6. So in this case here, knowing that the first roll is even did not have an impact on the probability of the sum being 7. It stayed the same. They're independent. All right, that concludes lesson 5. We're going to expand upon this in the next lesson with Bayes' theorem. As always, if you have any questions, please don't hesitate to reach out via email, office hours, discussion board. Thank you.